So my presentation today is about the physical science basis of how we know climate change is real and that humans are the main cause of it. Before we dive, before we dive into the core of the content, I thought I would share some basic concepts that are really important for putting the science into context. One of them is the difference between weather and climate. And so weather usually refers to short-term changes in the Earth's atmosphere, such as in the temperature, humidity, or precipitation. It's typically localized and refers to a specific time and place, whereas climate is really a lot more about the longer term trends in weather. And so it's defined as the statistics of weather and traditionally measured over a period of about 30 years and longer. And it looks at the mean and average weather, but also the variability within that weather. And so looking at changes in seasons and longer term trends and such things. And so that's the first distinction to make, the difference between weather and climate. And then the second is the difference between climate change and global warming, which are sometimes used interchangeably, but are two separate things. And so climate change, as you would expect, looks at the changes in climate over the longer term. And this is referring to changes that persist for decades or longer. And so it's not short-term changes on the scale of 5 or so years. It really is the long term, and it goes back to the beginning of Earth's history. In contrast, global warming is a specific phenomenon that refers to the heating or increase in temperature of the Earth's surface, and that's both the land and the water surface. And this heating is measured relative to a particular temperature at a particular period in time, and the period in time that's usually used is the pre-industrial period, so from about 1850 to 1900. So really, to summarize, global warming is a result of the climate changing, if that helps put it more into context. So the Earth's climate system is one of the kind of core concepts to understand in terms of the dynamics of climate change. And there are a few components of the climate system, 5 major ones. There's the atmosphere, the hydrosphere, the cryosphere, the biosphere, and the land surface. We'll talk a little bit more about the atmosphere in the next slide and the role that it plays. But for now, this gives you an overview of the different components, the interactions and processes between them. And so the hydrosphere refers specifically to the oceans and seas, the saline water from oceans and seas, as well as fresh water from rivers and lakes, and subterranean water, so groundwater as well. So anything that's liquid is in the hydrosphere. The cryosphere refers to the ice, the sea ice, ice sheets of Greenland and Antarctica, the glaciers and snowfields, permafrost, anything that's more on the frozen side of things. And it's particularly important to the climate because of its ability to reflect solar radiation. And so as we dive into the dynamics of the Earth's energy balance, that will make a bit more sense. And then outside of, or in addition to the cryosphere, there is the Earth's land surface. And that is important for it controls how the energy received from the sun is returned to the atmosphere. And so some energy can be returned as long wave infrared radiation, which as a result of the heating of the land surface and having that heat radiate back up into space. But some energy is also returned as water through evaporation and evapotranspiration from the soil and plant leaves, for example. And then the biosphere is kind of the last element in the climate system. And this has a really important role to play in the composition of the atmosphere, the chemical composition of the atmosphere, especially because it influences the uptake and release of greenhouse gases. And so, for example, the forests store significant amounts of carbon from carbon dioxide, and so are really important in the carbon cycle and in absorbing excess carbon from the atmosphere. And so to understand a little bit more about the structure of the atmosphere helps us understand why climate change is happening and how global warming is occurring. There are three main layers in the atmosphere, starting with the troposphere down here, which is the layer that is closest to the Earth, and it extends about 10 to 18 kilometers above the Earth's surface. And the greenhouse gas effect mostly occurs within the troposphere. Above the troposphere is the tropopause, which is a transition zone, and then the stratosphere is the next layer up. And so those two layers are really, they hold the bulk of the atmospheric mass. And so 80% of atmospheric mass, excuse me, is in the troposphere, whereas almost all of the remaining 20% is in the stratosphere. And then there's trace amounts in the mesosphere as well. And so that 80% of the atmospheric mass comprises of these gases mainly. And so you can see that our atmosphere is comprised mainly of nitrogen and oxygen, which together comprise about 98% of the total volume of gas in the atmosphere. And then we have water and argon, which are also, you know, more than zero. But what's interesting to note is that the major greenhouse gases that we're concerned about only occur in trace amounts in the atmosphere. And so their impact is really quite interesting relative to the presence in the atmosphere. And so what exactly is going on? Before we go into that, we also need to understand how the Earth works on a typical basis. And so the Earth's natural energy balance. And so there are kind of two aspects to the Earth's energy balance. There's the incoming solar radiation, and then there is the outgoing solar radiation. And the difference between the incoming radiation and outgoing radiation is known as the energy balance or radiative forcing. And so in equilibrium, the energy that's coming into the system is exactly equal to the energy that's going out of the system. And that's what this figure shows kind of at the top here, which is net energy in minus net energy out. And as you can see, there's a lot of internal dynamics that are occurring within the system, and that helps to explain what's a little bit more what's going on. So in the incoming energy, part of it is reflected by clouds, aerosols in the atmosphere, but another part of it is reflected by the surface, which, as I mentioned earlier, the ice sheets play a huge role in that because of their reflectivity. And so the total percentage that is reflected, directly reflected back to space is about 30% of the incoming solar energy. The rest is split between being absorbed by the surface and being absorbed by the atmosphere. And so that's the dynamic in the incoming solar energy. And then you go to the outgoing area, and then you start to see some really strange numbers. And the question is, what's going on? Well, what this figure shows is the net difference between energy, but it doesn't capture the time lapse. And so this net in and outgoing energy is on a longer term basis. And so there is, in fact, some accumulation down here beneath the atmosphere of energy once it comes in from the sun. And so, as you can see, the total amount of surface radiation is quite substantially more than what's being absorbed by the surface. And that's because of this action here, which is back radiation from the atmosphere because of greenhouse gases. And so what's happening is that the energy absorbed by the surface from back radiation plus the energy absorbed by the surface from the solar energy radiates back out in different ways. So it radiates through kind of a general surface, 350 out of that 390 goes up into the atmosphere. About 40 goes straight directly through and to the clouds. And then there's this radiation from thermals and evapotranspiration. What's important about this figure is not so much the numbers, but the relative absorption. So you can see that the amount of energy that's absorbed through back radiation is almost twice as much as the amount of energy that's absorbed from direct solar radiation. And this is because of greenhouse gases in the atmosphere. And so we'll speak to that a little bit more on the next slide. But what's important to know is that right now, the planet is not in equilibrium. And what's happening is that there is more energy coming in than going out. And so there is a net positive energy imbalance, which the IPCC estimates to be about 1 watt per meter squared. So what is the greenhouse effect? The greenhouse effect is this phenomenon that has been in existence, a natural phenomenon that has been in existence for a very long time, and it's what keeps the Earth at a habitable temperature for human beings. And so it happens because the trace gases in the atmosphere, so the ones that we know, carbon dioxide, nitrous oxide, water vapor I'll come to specifically, but these gases allow the incoming solar radiation to get directly to the Earth's surface, and that warms up the Earth's surface. But the outgoing radiation, long wave infrared radiation, part of it is absorbed by the greenhouse gases. And when it's absorbed, some of it is emitted to space and some of it is reflected back to the surface, which is what the back radiation was in that figure on the last slide. And so the greenhouse gas effect, the greenhouse effect really is the effect of the Earth feeling like a greenhouse. So having this layer of gases that act to retain heat on the surface. Now, when that goes wrong, that's when we have an issue, which is what's going on now. So increasing the amount of carbon dioxide increases the amount of heat that's held in the atmosphere. And so what we're witnessing is an enhanced greenhouse effect and not the natural phenomenon that has been in existence since time immemorial, I guess. And so to help put this into a bit more perspective as opposed to more of the qualitative understanding, this graph shows the absorption bands for different greenhouse gases. So the absorption of electromagnetic radiation by different greenhouse gases. And what I'd like to point out on this is there are a couple things. So this red area here is reflective of solar radiation. And so what's coming in, and this blue is reflective of what's going out. Now, the shaded in red area is the amount of solar radiation that's transmitted. So that's what we can, that's what's coming in, that's what we can measure, that's what's not absorbed. And so similarly, the amount of blue is what is being transmitted back out into space. And so this graph here is the inverse of the top graph. And so you'll start to see, you know, the opposite pattern in terms of what's being absorbed versus what's being emitted. And so, for example, this blue area directly reflects, this white area directly reflects the blue area. What's important about this figure, there are a number of things to note. Water vapor and carbon dioxide are big things, so I'll come back to that. But one thing that's also very interesting is how oxygen and ozone work. And you can see that they absorb quite a bit of the radiation in the UV band, which is good for humans because it means less harmful UV rays are getting down to the Earth. So that's, you know, something interesting to note. The other interesting thing is the amount of absorption by water vapor and carbon dioxide. And so you can see that water vapor holds substantially a large amount of the outgoing thermal radiation in both the kind of the long wave side and a little bit on the shorter wave side. And then the next highest is carbon dioxide. So carbon dioxide also holds a large amount of thermal radiation. Now, the difference between these two and the role they play in the climate system is discussed a little bit more on the next slide. But what's important to note is the temporal, I guess, characteristics of water vapor and carbon dioxide. So by temporal, I mean kind of the time frame. So water vapor is a short-lived gas in the atmosphere, which means that it's flushed out fairly quickly on the scale of days to months. And so it doesn't accumulate in the atmosphere. So even though it's able to absorb quite a large amount of heat and it's more abundant than carbon dioxide, it's flushed out fairly quickly. Carbon dioxide, on the other hand, is a long-lived greenhouse gas. And so what it does is it accumulates in the atmosphere, and so it doesn't disintegrate as fast as water vapor. And so that's why it plays a different role to water vapor in the climate system. And those roles together are really some of the most important dynamics in understanding what's going on with the climate. And so carbon dioxide is referred to as a forcing, so a climate forcing or radiative forcing agent. And what this means is that it has a direct influence in changing the energy balance of the Earth's system. And so imagine the level of carbon dioxide to be the volume control on your phone if you want to turn up the volume. The up button would be carbon dioxide. You get a very instant reaction. A feedback, on the other hand, is a process that can either intensify or weaken the initial forcing. So in this case, in the case of our climate, water vapor acts as a feedback to intensify the effect of carbon dioxide heating up temperatures. And so imagine a feedback would be the Bluetooth speaker that you you connect to your phone so that the sound gets a lot louder. And that's the role that water vapor is playing in the climate dynamics. And so this is the feedback loop that shows the influence of carbon dioxide as a forcing agent and how it impacts water vapor in terms of the feedback process. And so an increase in carbon dioxide concentration results in an increase in the Earth's temperature. That's a relationship that has been established, long established. And this increase in the Earth's temperature increases evaporation from land and water. And this evaporation increases the amount of water vapor in the atmosphere because warmer air can hold more moisture. And so now we have more water vapor in the atmosphere. And if you remember, water vapor is particularly good at holding in heat. And so this water vapor holds in more heat, which increases the greenhouse warming, which increases the global temperature. And so there's this positive feedback loop that just keeps reinforcing itself, triggered by the increase in carbon dioxide concentration. So the next question is, how do we know carbon dioxide is increasing? What is the evidence for this? There are two sources of evidence. There is paleoclimatic evidence, and there are instrumental records, which are the observed measurements that we've made over time. And both of these are necessary because we're making a comparison between levels throughout the Earth's history and present day levels of carbon dioxide. So for the paleoclimatic evidence, these are a few photos. This is a deep ice core, some tree rings, and I think this is a sediment sample from the deep ocean. But really, these can be analyzed to look at trapped gases, which gives us an idea of the climate at the time those ice cores or any of these other evidence were formed. Tree rings can be counted to determine age. The thickness can be looked at to determine the optimal growing conditions, to get a better sense of the growing conditions of when the trees existed. And then sediment cores usually contain the remains of organisms, sediment cores and fossils actually, contain the remains of organisms that can indicate changes in past climate, because each particular species has a kind of a specific range of conditions that it can be alive in. And so that's how this information is used to determine the past climate. And then we look at the instrumental records that we have. And so we have data on surface air temperature, ocean heat content, sea level, sea ice. And these are the instruments that we're using to get all of these measurements. And so weather stations, weather balloons, Doppler radars, and weather satellites. And so all of this information is collected, and what it gives us is this graph, which I'm sure many of you have seen or have seen something similar to it, which shows the historical carbon dioxide level based on paleoclimatic evidence and the present day carbon dioxide levels. There are a few interesting things about this graph other than the extremely shocking rise at the end. So you can see that the climate has varied quite substantially over the last 800,000 years. But you can also see that the maximum kind of level of carbon dioxide concentration has been around the 300 parts per million mark. The other thing to note in kind of the historical timelines is the duration over which the concentrations change. And so the scale, we're looking in hundreds of thousands of years, and you can see that, you know, for this kind of dip in climate, you're looking at approximately 100,000 years. So we're looking at 10 decades for the levels of CO2 to change. And then we go to this little area here, which is indicative of, you know, present day timing. And you can see that there is a almost straight line increase in the concentration of carbon dioxide in the atmosphere. And so the question is, what's going on here? I mean, we have the records to confirm that this is happening, and we need to understand why. And before we dive into why and how humans are really the factor, the other thing I wanted to highlight is that human civilization has been around for 10 to 12,000 years. Those are the estimates that we have at present. And so really we've been around mostly when the climate has been stable, and we haven't really experienced any of these wild variations in carbon dioxide levels. So the next question then is, how do we know that the planet is warming? Because we know CO2 levels are rising, so how do we know that that's linked to a warming planet? Well, there are a number of indicators that researchers and scientists expect to see if the world was warming, and this graphic shows 10 of them. And so there's the indicators and the direction of what they'd be doing. So for example, if the Earth was warming, we would expect to see the air temperature near the surface, so near the troposphere, increasing. We would expect to see the ocean heat content going up, humidity going up. We would expect to see the volume of sea ice going down, glaciers, snow cover. So this is kind of what we would expect to see. And of course, according to the instrumental record, we're seeing those trends. And so the air temperature, humidity, ocean heat content, all going up, the snow cover, glaciers, sea ice, all going down. These figures are from a 2009 report from the NOAA from the US, and the data sets are superimposed. So they're independent data sets that have been analyzed by different groups, and they've been superimposed on this graphic. The report is called the State of the Climate Report. And I don't know that they do an exact version now, but this kind of gives a really good overview of the trends that we were seeing in the 2010s, really. And so, I guess the conclusion is really that what we expect to see is what we're seeing. And in the most recent IPCC report, it's been confirmed that the global surface temperature has increased about 1.1 degrees since pre-industrial times. And this is definitely due to the increase of greenhouse gases in the atmosphere. And so the other question is, how do we know humans are the main cause? And so to answer these questions, there are multiple, again, separate lines of evidence that are used to support the claim that humans are the main cause, and that human emissions are the main forcing factor in changing the global climate. And I won't go through all of them. We can come back to them and discuss them individually if we'd like, but some of them are a bit more pertinent and easy to understand than others. This one I like, and it's really simple. It basically shows the increase in CO2 emissions relative to the increase in atmospheric CO2 levels, and you can see that the trends are almost exactly the same. But again, it's only one line of evidence. And so there's always questions as, how do we know humans are causing it? And so there's these other lines of evidence that we can look at. And one of the ones that I find most, I guess, most arresting and really most obvious is that the type of fossil fuel, type of carbon dioxide in the air is specific to fossil fuel carbon. And so the carbon atom has different isotopes, so very chemical, but different number of neutrons in the center. And so there's carbon-12 and carbon-13. And plants have a lower carbon-13 to carbon-12 ratio than in the atmosphere. And so if the increase in carbon dioxide that we're seeing in the atmosphere was due to fossil fuels, which are plant-based, then we would see the ratio of C13 to C12 falling. And there have been studies that show that this is indeed the case. And so we're seeing that the fingerprint of carbon dioxide in the air is consistent with the fossil fuels that humans are burning. In addition to that, we're seeing that there's less heat escaping to space at the exact same radiation magnetic waves that carbon dioxide absorbs, and that the heat returning to Earth is also at the exact same radiation, the wavelengths that carbon dioxide absorbs. And so there are all these other elements of supporting evidence that indicate that humans are the main cause, and these are all things that we've observed and can be measured. On the flip side, there's also the modeling side of things and what that shows us. And so this is a kind of an overview of the observed change in global temperature. And I will flag that this is in degrees Fahrenheit. So no panic, we're not above the 2 degrees yet. This is in Fahrenheit. And so as you can see, if the models are set up to only look at the natural factors, there's no way to replicate the observed increase that we're seeing. But if the models incorporate both natural and human factors, then we can see that the observed measurements match a lot more closely. And so what are these factors that we're looking at that allow the models to be accurate in terms of replicating the observed measurements? This is from the IPCC report, the 5th assessment report. I'll come to why the 6th assessment report isn't there a little bit later, but this shows the different forcing agents, so the things that can have a direct impact on the climate, versus the anthropogenic forcing agents versus the natural forcing agents. And as you can see, the anthropogenic forcing agents exceed the natural by a large margin. You can also see that there are cooling effects. So there is negative forcing from aerosol and cloud aerosol radiation, aerosol cloud interactions. But again, those are outweighed by the positive forcing and the greenhouse gases. So a couple of things when we start to look at really this figure. First thing to note are the error bars. And so you can see that there are quite significant margins to the values that are put on this figure. And so for the total anthropogenic forcings, you can see that the bar goes anywhere from 1.1 to 3.4 approximately. And so if you remember a little bit earlier in the slides, the number that we're working with right now is 0.8 to about 1 watt per meter squared. And so the estimate that we're working with is at the lower end of the error bars. And so it's not likely that we're experiencing much lower, but it's possible that it could be higher. So the estimates are conservative at this point. Oh, yes. Okay. So before we dive into the next slide, I think the summary of all of this is that while there are uncertainties in terms of the exact level and magnitude of radiative forcing, the fact that the climate is changing and humans are the main cause is not in doubt any longer. But it's good to understand how the uncertainties are classified and what the rationale is, and how the IPCC structures its reports. And I picked the IPCC because they're usually the most well-known in terms of climate science, but I think it's also useful to clarify their role and exactly what they do and what they mean when they say particular things. And so first off, the IPCC does not conduct its own research. What it does is it synthesizes all the existing literature on climate science, and it it identifies areas of scientific agreement, the strength of that agreement, and also where further research is indicated. And so it does this through the use of confidence levels and likelihood. So as you can see in this corner of the table, if there is robust evidence for a phenomenon and there is high agreement within the scientific literature, then the level of confidence with which those statements are made is pretty high, versus if there is low agreement and limited evidence, the level of confidence is pretty low. And so when you see the IPCC statements and you see medium confidence, low confidence, high confidence, this is what they mean. They're referring to the agreement in the literature and the evidence that's available. And then the likelihood of outcomes and occurrences is also another dimension of how uncertainty is classified. And so really, if there is virtually no uncertainty, say, to the dynamics of a particular geophysical process, so the heating, the relationship between carbon dioxide and increase in temperature, the IPCC can say with almost virtual certainty that the climate is heating up because of carbon dioxide emissions and concentrations. And then you can also get these more broad statements about as likely as not, which is really, we're still figuring it out, and there's as much of a chance of it being true or not. And so I appreciate this, because what this does is it directs researchers to focus efforts on places where there is more uncertainty and where the statements aren't as supported by the evidence. And so what does this all mean for the future going forward? Also important to understand what the science and what our climate future is looking like, and to clarify exactly what these representative concentration pathways show and where they give us room to improve. So the representative concentration pathways are 4 different pathways that reflect different levels of greenhouse gas emissions and atmospheric concentrations and other emissions, so air pollutant emissions and land use. They also incorporate climate mitigation strategies, which is very important to keep in mind. But what I wanted to highlight with regard to uncertainties on this slide and their representative concentration pathways is the fact that the RCPs are exactly what they say they're representative. And so they're not precise estimates of exactly what will happen. They're kind of the average that's shown, reflected in the literature. And so this gray area here is the range of different carbon dioxide values over 1,000 that the literature is seeing. And RCP 8.5 is kind of a line in the middle. And you can see that for the remainder of the RCPs. So this portion of the graph is not set in stone, but it gives us an idea of the possible scenarios we could face if CO2 emissions went in these directions. In terms of the mitigation options and mitigation actions, I think that's really important to note and to keep in mind when looking at these, because the projections are based on different levels of mitigation. So for example, RCP 2.6 is based on very, very stringent carbon dioxide mitigation actions. So basically just stop using all fossil fuels now. And the idea is that if that happens, there will be a continued increase until at least the mid-century from gases that are already in the atmosphere, and then it declines. That's not happening. We know that's not happening. And so that's kind of a very low likelihood scenario. The 2 medium scenarios are RCP 6 and RCP 4.5. They have medium level mitigation measures. So we do a decent amount of things, and it's not as bad as it could be. And so eventually the levels of carbon dioxide stabilize and we don't overshoot. And you can see that the differences in temperature we would expect from the different RCPs are quite wide ranging from 1.5 to 4.9. RCP 8.5 is the one where we do nothing and carbon dioxide levels keep rising. And that's I don't know if that's the worst case scenario, but it's definitely the business as usual case that we're experiencing. And so this really shows how much opportunity we have to change the direction of the projections. So to zoom out a little bit, and I'm kind of getting to the end of the presentation, what are the main uncertainties? What do they mean for our future going forward? What can we do? Really, the three main buckets of uncertainty are the uncertainty regarding the future emissions, which I just talked extensively about. There's the scientific uncertainty in understanding exact geophysical processes. And so those are the error bars, for example, on the aerosol cloud and aerosol radiation forcings in the IPCC figure. And so there's wiggle room. We don't know exactly the amount, but we know the general trend of where things are going. And then there's also natural variability in terms of variability in weather patterns as well. And I thought this quote was a really good way to summarize the impact of the different uncertainties. And it basically highlights the fact that what the amount of carbon dioxide we emit over the next 50 years determines the extent to which our climate changes. And really what we choose to do and how quickly we do it is the factor that matters really the most. There's a really great video, but I won't show it now. I'll keep the link in here and share it if anyone wants to see, that looks at how the scientific uncertainty has been used to divert the discussion on the level of certainty that does exist about global warming and climate change. And so what can we do? Well, there are two things that we need to do. We need to invest in climate adaptation because there are already impacts that we're dealing with at the moment, and there are impacts that are going to continue into mid-century. And so we need to invest in a lot of climate adaptation efforts and policies, but also climate mitigation, because that determines really how bad or how good the future ends up looking. And so I wanted to highlight the policies and actions are very essential. And I think I've talked about that quite a bit, but I also wanted to highlight the scientific research that could be used, that could be beneficial. And so there's lots of talk about different ways in which we can modify the amount of solar radiation, or we can remove carbon dioxide from the atmosphere. And these are areas of important research. The IPCC report actually does have some information on the literature that's looking into solar radiation modification. There's lots of medium and high confidence about good and bad things, but it's being looked into, which I think is good and useful to have as a backup. And the same with carbon dioxide removal. So there are a lot of effects and feedbacks in both of these that aren't well understood. And so they would benefit from a lot more research and discussion. And so with that, I'm going to end. Thank you for your patience. And